Okay. Hey, so we continue with the second speaker for today, who is Alessandra Gnecchi, who is joining us from Padua, and she will talk about quantum gravity through the quantum black hole lenses.
I think I added a quantum with respect to the talk I gave in the abstract. Thank you very much for organizing this workshop and allowing me to present my remarks here. It's been very interesting and there's been a lot of discussions. I found it very exciting to really have a framework where to go back to all we know about quantum properties of gravity and how can we continue develop ideas from there. So thank you very much to the organizers. I will not just focus on holography. My talk will be divided in two parts because on one side, both parts somehow are motivated from how important I think black holes are and have been in pushing our understanding of gravity. I will be working or discussing this in the context of string theory, and holography is one of the main successes of string theory, where we have used black holes and applied our theory to understand black hole physics better. But I will start with some more examples on the context of the Swampland program, because I think that it's very, very important to exploit our knowledge so far to the case or the context of effective field theory. And given there's been a lot of interest also this week on these discussions, I think it's not bad to give some more examples. Yes, why do I work in string theory? Because it's an example of UV complete theory of gravity, which contains classical vacuum backgrounds as solutions of its equations of motion. In addition, I want to work with holography because I can use a DSCFT, as was mentioned in the talk before, to define quantum gravity on a curved background. I can define it at the full quantum level by being the CFT theory dual to it. Moreover, if I want to understand black hole evolution in the recent year, it's become more and more relevant to understand the structure of entanglement of fields on space-time. And one way that holography has been very fruitful so far is to give prescription on how to compute entanglement entropy of quantum fields. So it seems like a nice framework where to address these questions. And there is a fundamental principle here in this kind of research, in both the Swampland and the applied holography research, is that we don't need to go to the Planck scale to probe quantum gravity effects. We all agree on that. And so we can focus and we must focus on deriving constraints from our UV complete models that give signature in the effective field theory. The signature can be experimentally testable. Maybe they can be predictions that we can even detect in gravitational wave experiments, but they can also be constraints at the fundamental level of the field content of our effective field theory or their properties. And this has been discussed a lot. When I talk about holography in string theory, let me tell you that this, for me, is one of the greatest success of string theory because it is a quantitative prediction. It's a quantitative realization. Holography had been an idea that started from black hole entropy discussions, but for the first time within string theory, we have a fundamental prediction. We can predict on the CFT side correlators from the gravity side. And in addition to this success, I think we also have to give to string theory the first example of let's say, in some supersymmetric context, a construction of black hole microstates from fundamental constituents of strings and brane. And so once we have the match between the microscopic entropy and the macroscopic entropy, we have one example of a UV theory that predicts fundamental microstates. But this is somehow on the microscopic level. This is black hole microstates, we may be able to resolve them or see them once we are in a full regime that is beyond the classical gravity regime. If we want to focus on the effective field theory side, we need to look either at semi-classical black holes or this approach called the Swampland program. And we've been talking so far this week a lot about looking for effective field theory and their properties. In string theory, I remind you, we are working in 10 dimensions or 11 dimensions if we're looking at M theory. And in order to make contact with effective field theory, we need to choose some compactification, and we need to build the low energy theory with ingredients that we choose in various ways. And we have so many ways to construct low energy effective theories, decide the geometry of the space and the dimensions we want to reach. We can construct a quantum field theory from D-brane constructions, and they're usually strongly coupled quantum field theory, but we can't get all that we want. We can only derive certain theories with certain properties from string theory. So it seems that these theories we can construct have striking properties that characterize them. So this hints at having not all the quantum field theories can be coupled in a UV to a theory of gravity. And if that's true, that means that maybe there are certain properties inside the string theory construction and formulation that are properties that are more general to any theory that admits a quantum gravity completion. And yeah, so this idea that the UV physics actually directly enters the physics in the low energy is a very well-known fact. And of course, once we have an effective field theory, it can get a UV completion that determines the effective field theory, that we know there is a relation. But a direct evidence in some quantities is what we call UV IR mixing. And this is quite a general phenomenon. In fact, think about the Bekenstein bound, for example. The Bekenstein bound is a bound that it's on the properties of the field in the CFT that comes once you start requiring that your effective field theory actually is an effective field theory that is coupled to gravity. Naively, if this was not true, then you can keep throwing quantum fields in a region of space-time until they collapse to a black hole, and then you'll get that the entropy of that system is the entropy of the black hole, thus violating the second law, because you would reach to a state with lower entropy. And since in general the scaling of the QFT entropy of fields in a QFT scales with the volume and not with the area. This was the first hint that when we're dealing with QFTs, we're actually overcounting the states. But you see that if we add this kind of bounds, UV cutoff like the Planck length and IR cutoff like the volume of your system start talking to each other. A more quantitative UV-IR mixing example is the Cohen-Kaplan-Nelson bound. Again, I'm talking about very well-known facts here. That tells us that the QFT entropy needs to be relation that is a UV-IR mixing. And in fact, this comes from the fact that not only you need to create black holes once you reach a certain energy, but you need to have a volume that is big enough to contain a black hole of that energy. So if you impose these constraints, you impose that the radius of the Schwarzschild radius of the black hole of that energy must be contained into your volume, then you have a constraint between the energy and the volume of that of your system. And so you put a relation between the UV cutoff and the IR cutoff. And this was the CKN bound. The maximum entropy states, you can see that in this context that they are already changing the scaling. They're now scaling if the lambda saturates this bound. You see that you've changed the scaling to area to the 3/4. So you're already correcting the way you count the fields in the quantum field theory. So pushing towards this idea that the naive scaling of quantum field theory at high energies could be different at high entropy. And let me tell you about the species scale, which is very important in the context of string theory, where you have a lot of towers of light fields that naturally can become light. Once you have well, for any effective field theory, the number of light fields below the cutoff lowers the gravitational Planck mass cutoff. And in fact, you have to consider these as your actually UV cutoff in an effective field theory that contains gravity. And in addition to the perturbative result that light fields correct the graviton propagator, there is a argument by Gia that tells you that actually, if you look at black holes, a black hole of charge n needs to decay, but can only starts emitting particles when the temperature reaches the energy of these states because of Boltzmann suppression, and it can emit at most all the energy that makes up for the mass of this black hole, and this puts exactly this bound on your UV energy cutoff. So you see that you have a lot of important constraints that are coming from the requirement that your quantum field theory that you're completely fine with is actually coupled to gravity. And so the lessons here are that we need to look for non-trivial signature of UV physics in the low energy theory, and they have to be our lamppost for building a theory, an effective field theory that lives in the landscape and not on the swampland. You see that black holes have been central in all these arguments I've made so far. And actually, my attitude has been to keep looking at black holes and try to extract as much physical properties as possible on our effective field theory. And so far, we know that we can give strong arguments in favor of certain properties we believe are fundamental properties of a theory of quantum gravity that rely on black hole physics. For example, we believe that any global symmetry needs to be broken once the theory is coupled to a UV complete theory of gravity. And the reason is that a global symmetry would not be conserved by a black hole evaporation, because in order to have conservation of charge, you need to have gauge fields that trigger the evaporation of charged particles outside the black hole. And because black hole can have any charge, then they can emerge and produce any other charged particle, then we are pushed to believe that there is a sort of completeness hypothesis in the spectrum of our theory. So all the charged particles need to be realized in our spectrum. Otherwise, I could just create them by merging black holes with different charges. And of course, the weak gravity conjecture tells us that in order to avoid the existence of remnants with a certain charge, like for example extremal black holes, we need to have in the spectrum certain states that are super extremal. So the ratio, mass to charge ratio, needs to be smaller than 1, with appropriate unit measures. And of course, the standard model fits all of these requirements, except for the fact that we have global symmetries in the standard model, and so at some point they will have to be broken. Why string theory fits well in this program? Because in string theory, once we look and try to construct an effective field theory, we naturally are asked to fix a lot of light fields. The problem of moduli stabilization is one of the first problem encountered in constructing effective field theories in string phenomenology. And so there's like a plethora of light fields that come directly in the theory, and we need to choose these moduli to fix a particular vacuum. And these moduli describe, in general, for let's say flat backgrounds, a moduli space. What happens when we move in moduli space? Of course, if we reach the boundary of moduli space, we know that the effective field theory there should break down. And since we have construction in the UV of these backgrounds, we can trace back the breakdown of the effective field theory in something going wrong in the full string theory. one of the first conjectures that fit into this string Swampland program was the Swampland distance conjecture, meaning there is a distance defined in terms of the moduli fields, such that once you reach regions which are at infinite distance from the vacuum you started with in moduli space, sorry, then your EFT breaks down because there is a tower of light states becoming light. And this infinite tower of states becoming light, according, for example, remember the species scale bound, is pushing our cutoff of the EFT to 0. So there's a breakdown of the EFT, and we're pushed to a different description of our theory. And there is a conjecture that's recently been put forward that in string theory, what's happening when you reach infinite distance in the modular space is that either you have a decompactification of a space-time direction, space direction, and so you need to change your effective description because now you're in a space with higher dimensions, or you reach a different, like, weakly coupled string theory description. So this is related to dualities. Maybe you're reaching a point in your modular space where the correct description or your EFT is given in terms of a dual theory. So the way this is phrased is that the masses of the tower of fields decays exponentially with the distance of in moduli space. This is related to the fact that the kind of constraints we're looking for are constraints that make sense once the theory is coupled to gravity. If we send the Planck mass to infinity and we decouple gravity, this constraint should become trivial. We don't want to constrain the EFT from other perspective. We'd really want to find genuine quantum gravity constraints. So we need always to look or investigate those properties and those behaviors that are consistent with the fact that our constraint will become trivial if L Planck goes to 0. Can we use black holes to probe infinite distance limit? I want to give a simple example just to give an idea of how we can use it and how it is important to make contact with the UV theory in understanding the breakdown of the EFT. And black holes, as I said before, can be constructed directly in string theory from microscopic constituents. Strings and brane give charge to the black holes that we see in 4 or 5 dimensions. What do? We start from the theory that has 10 or 11 dimensions. In this case, I stick to 10. And we decide that 4 dimensions will be our non-compact space. And there will be some dimensions that will be compact. And if we, guided by supersymmetry, want to find a supersymmetric vacuum or a vacuum compatible with supersymmetry because of simplification of certain equations, we have particular constraints on these internal geometry. We call it internal because that's what will become compact. We have to think about our black hole in 4 or 5 dimensions living in this space. But at each point in this space, there are actually internal directions that are so compact that do not play any dynamical role in the effective field theory. But this compactification leaves in the lower dimensional theory an effective theory that contains scalar fields, which are basically parametrizing all the ways we can deform these internal geometry, preserving supersymmetry. And to give you 2 simple examples, what does it mean to look for black holes in these effective field theories? In 4 dimensions, I'm looking at compactifications with a certain supersymmetry, and I'll stick to n equal to 2 extended supersymmetry. The theory will be supergravity because I want to have a dynamical classical action for the metric. And black holes will be solutions of this action. Why do I forget all the fermions? Because I'm looking for a background with 0 fermions. And in addition to my gravity action, I have scalar fields, as promised, coming from geometrical directions in the compactification. And I have abelian fields. So naturally, from string theory, I get theories where any kind of Reisner-Nordstrom black hole can be realized pretty naturally. And I can even have magnetic charges. A more simplified way is the Einstein-Maxwell-Dilaton theory. This is a more simple one-field model that maybe scares less than these complicated couplings, etc. But the idea is the same. I'm going to have certain scalar fields which are coupled to the metric, and they will give me a black hole metric which can have finite temperature, and this is a generic way of writing a static black hole. Sorry. These solutions have been studied a lot in the string theory literature because at zero temperature, like every Reisner-Nordstrom black hole, they have a universal near horizon geometry, which is ADS2 times S2. But this geometry not only is universal, it is a supersymmetric vacuum. So for people that were asking why is anti-de Sitter so important in string theory, well, anti-de Sitter is very important in any supersymmetric solution you want to get in a supergravity theory. Anti-de Sitter factors preserve supersymmetry in any dimensions, and they appear naturally as near horizon of black holes. The Bertotti-Robinson geometries for Reisner-Nordstrom is the prime example. We have ADS2 times S2, and in string theory and you can have even examples of other kind of topology horizons if you work in anti-de Sitter. But let's stick to the vanilla case. The black hole of the entropy of this black hole has a very simple expression in the case of zero temperature supersymmetric solutions. It is described by this quantity, and you can see that in the value of the entropy, there is the value of the scalar fields at the horizon. So that's how the scalar fields that come from the compactification are coupled to the physical properties of the black hole. At infinity, this quantity, which is the central charge of the n equal to 2 symmetry preserved at the horizon and at infinity, gives the mass of the black hole. What do I have to do here, though? I have to choose the value of the scalar fields at infinity and the value of the scalar fields at the horizon. Sorry, the value of the scalar fields at infinity I can choose. They are part of the moduli space of my compactification. They are constants. And they run because of the supergravity equations, they run to a different value at the horizon. What's important is that in the supersymmetric case, which was very well studied, it's the story of the attractor equations, these scalar fields are fixed to a certain value that only depends on the charges of the black hole. In fact, you could have asked, sorry, how come that the black hole entropy depends on continuous parameter, which are these moduli? It does not. Because of supersymmetry, this entropy is given by quantized quantities. And in fact, it is what is matched in the microscopics with an integer number of microstates. But what's happening here that's relevant for our story is that the scalar fields are running in spacetime. By constructing this black hole solution, I'm forcing the scalar fields to run in moduli space from infinity to the near horizon. So there's already a distance in moduli space that I'm somehow forced to traverse because of the existence of this black hole solution. I also have now one parameter, physical parameter, the entropy, and I can also add the temperature, that is relating a physical property of the black hole to the scalar fields that have a UV origin. And this entropy that depends on the charges, if I change something in the UV theory, like I make certain cycles large or small, this entropy can become very large or very small. So there was an attempt at actually defining a distance in terms of the entropy. And these people asked, what happens if the entropy becomes very big? Can we identify a tower of states that become light? What we did also is, and what one can say is, what happens then if we also go at finite temperature? Because this was the story at zero temperature, but we can heat up the background, the black hole, and easily come to a finite temperature solution. And actually, if you think about the Schwarzschild black hole, there is both with entropy and temperature, they have a dependence on physical parameters of the black hole that we can use. And the first thing to look at is that actually there is this frequency of Hawking modes related to the temperature are modes that decouple when Planck goes to zero. They all become infinitely heavy modes. And this is interesting because if you look at the Unruh temperature, the Unruh temperature has modes that depend on the acceleration of your observer with respect to static observer, and that does not decouple if you look at if you send the Planck length to zero. So it's not trivial to find the quantities that are proper, that have a proper gravitational origin. And so it seems that this hints that like actually the temperature and entropy have something to do with our background being a gravitational background for the black hole. I showed you black holes that were charged that actually are of the Reisen-Nordstrom kind, because if you only work with Schwarzschild, of course you have only one parameter to tune, so you cannot really have any analysis of both the T and S parameter space. You can in supergravity, and again, one of the power of string theory is that you can do a lot of calculations explicitly. We can fix a model and write down this action with all the couplings specified. And in particular, if you take this model, the STU model, which has 3 complex scalar fields, you can easily compute a quantity, which is the product of these 3 fields, which at the vacuum gives the volume of the internal dimension. This volume is what appears in front of the 6-dimensional Calabi-Yau that you have chosen for your compactification. But then if this combination of scalar fields gives you a volume that has to do with the internal dimension, it means that I can parameterize with this combination of scalar fields a mass of Kaluza-Klein states associated to an internal dimension becoming well, a small internal dimension, or dualizing them, I can find winding modes. When the Kaluza-Klein states become light, the winding modes are heavy, and vice versa. But then you see now I have a parameter, I have a volume that is defined in terms of the low energy effective fields that parameterize something that tells me what's happening from the UV point of view. And if you write down for this model, fix your charges in order to have a solution that you can write down explicitly that has a supersymmetric limit, but that's secondary. You can write down the entropy and the temperature explicitly in terms of these charges, which are your parameter. You can tune these charges by choosing different cycles in the internal in the UV theory. And the moduli fields at infinity. So you fix the vacuum once at Minkowski vacuum, and then you see what happens at the horizon. Because the horizon of the black hole, depending on the charges, can give you a large or a small volume for the internal dimensions. And so you can see that we can analyze what happens to this quantity in the ST plane. And this is what happens. If you look at all the possible solutions that are charged black holes with this set of charges, you basically span this purple region. This line here is the Schwarzschild limit, where the black hole is uncharged. And you see that you have an infinite entropy, an infinite temperature, and the zero entropy, zero temperature limit. And you can check that, for example, if you send the T1 limit, once you send the temperature to zero, but you keep T finite, there is actually Kaluza-Klein tower of states that become light because your volume goes to infinity. And in the other, there's other behaviors that you can trace, and you can do the same analysis by following, by studying the temperature instead of the entropy limits. And you do recover certain limits. For example, when S and T goes to zero, this is a small black hole limit, and you expect some stringy correction coming in. Of course, this is the analysis of this limit is bounded by your supergravity effective field theory, so that itself breaks down. But this is your connection to the the UV. And another observation I want to do is that we've built black holes from string theory, but what we've used to build them is branes and fluxes, potentially from the higher dimensions. And this is not very different from what we used to construct black backgrounds that are de Sitter backgrounds or anti-de Sitter backgrounds. And so it seems that if we look at this behavior, they should have the same origin, these limits, that we have when we look at de Sitter vacua. And in fact, the gravitino mass on the Sitter backgrounds has exactly the same form of the black hole entropy for an electric black hole. So there are quantities that determine the that make you move a moduli space that have exactly the same realization from the supergravity point of view. In addition to that, the black hole potential that gives you somehow the entropy of the black hole is very analogous to the d term potential that gives you the cosmological constant for anti-de Sitter. And in fact, for de Sitter, there is an anti-de Sitter, there is an ADC, anti-de Sitter distance conjecture, that tells you that if you try to move from an ADS vacuum to a Minkowski vacuum, you will have a tower of states that become light, scaling with the cosmological constant. And this is basically the same origin as this idea that if you move at infinite entropy limit, you will have the same tower states that become light because of the same origin of fluxes in the higher dimensions. And so having a UV realization of your setup helps you also to understand what is the physical meaning of the results and the limits you're studying and you're seeing in effective field theory. This is also interesting. I said that we're taking the we're changing the charges of the black hole, and then we go to limits of infinite entropy where we have a breakdown of the EFT because there's a infinite limit of this volume. Actually, this volume also parameterizes the gauge coupling in your Lagrangian. And so you can see that in the limits where these volume goes to infinity, you do have an effective gauge coupling that goes to zero. And so the breakdown of your EFT also manifests as a restoration of a global symmetry that was before a gauge symmetry. And so there is a relation between different behaviors like restoration of global symmetries, towers of states becoming light, that are all linked together in these examples. And again, the point is that we are using an explicit string theory construction, and that is, for me, what is important in the string landscape and string Swampland program, that we do have control on the UV, and we can go back and pinpoint the origin of what we see in the EFT. Okay, I will continue now and with the part that has more contact with holography. I said before that the power of string theory lies on one side in the UV to understand black hole physics. And the very first examples were actually the construction and counting of black holes microstates. But this is actually also related to holography, because I've talked about black holes so far in the effective field theory that had a Minkowski vacuum. One could ask, okay, if holography is telling me that a gravitational solution has a CFT dual, why cannot I build a black hole that now lives in an anti-de Sitter space and just for fun count the microstates in that background? And for the count, this was what was actually done, although for a long time it was not so easy to find a black hole in anti-de Sitter. Why? Because in Minkowski, I said you have a moduli space for your vacuum, and you have all these moduli fields, these scalars that you can choose their value. They're constants, and you can move in moduli space. They all correspond to fine vacua. If you want to construct an anti-de Sitter vacuum from string theory, you don't have that freedom. The anti-de Sitter vacuum in string theory preserves some supersymmetry, so it's an additional constraint that fix the scalar fields already. So we don't have much space to also find a value for the scalar field that are fixed at the horizon of the black hole. So instead of moving and flowing from Minkowski to the near horizon and having constraints on the near horizon because of extremality and supersymmetry, now we have many constraints. So it's much more difficult. It was done nonetheless, and it's a very interesting line of research that uses techniques like localization and supersymmetric localizations, and has pushed a lot also the ADS-CFT tests of ADS-CFT in the recent years. Well, now, if we move from these black holes that have nice properties, like they preserve supersymmetry, we can build their microstates, and we think more conceptually, okay, what about semi-classical evolution of black holes? Do we understand that? Do we have a framework that allow us to understand what happens to an evaporating black hole? If we go back to Hawking, this is the first step to consider a classical black hole semi-classical. We just consider quantum fields on top of a classical black hole background. And do we have a framework where everything goes right in this description? And it's also a possible panel question. So maybe I don't want to give a definite answer. I think there's a lot to learn still there, even though so much time has gone by. Why? Because we need to build a background. We don't have all the ingredients there that allow us to satisfying describe black hole evaporation. But let me tell you some more why I think that's the case. Quantum fields and the black hole can be at equilibrium with the Hawking temperature. They manifest entropy that I've talked about so much so far. However, in this description, we need to ensure that our theory preserves a unitary evolution of the system. Once we consider a black hole that's built by collapse of quantum states, then we are sure that the states we start with are a pure quantum state. And because of singularity theorems, and we know that these fields will eventually build the black hole. This black hole, built by quantum states in a quantum vacuum, will start radiating. Once it starts radiating, it will reach a final state that we can only describe with final full irradiation, radiated back to the universe. And these states better also be a pure state. At every point of this evolution, the state must be in a pure state. Now, take an initial state of infalling quantum matter. This state is a pure quantum state. It's described by a density matrix that has this form, by definition of pure state. However, after the formation of the black hole, there is a new part in the system, which is the black hole interior. Now, the black hole interior now is a subsystem of the full system, because the full system that was a pure state now is part the interior of the black hole and part the quanta that are being emitted at black hole radiation. So in order to have a full pure state, each substate or subsystem is actually not a pure state. It is a state that is mixed and it is entangled with its complement. There is a quantity that quantifies how not pure, how mixed this state is, and this is the von Neumann entropy. So what we do is to look at the system, black hole plus radiation, and as an observer that lives outside of the black hole, we do not have access to the subsystem interior of the black hole. We only have access to the exterior radiation. And so whatever quantum measurement we make, or computation or calculation we do, we will have access to the reduced density matrix of this state. We need to trace over the information we do not have access to, which is the interior of the black hole. And that produces this von Neumann entropy and a reduced density matrix. Yes. Maybe I switched the side of the two slides, but the point is that eventually what's going to happen? It's going to happen that the more time we wait, the more radiation is emitted from the black hole. What does it mean? It means that the entropy, the entanglement between the two systems grows. You can imagine that if I have just a few quanta that comes from a pure state, these few quanta are entangled with the rest of the system, but they're really few quanta. So their entanglement cannot be large. The more quanta I get, the more the entanglement entropy grows. It will reach a maximum when the two subsystems are comparable in size. The information stored in one subsystem is comparable to the information stored in the other. And that's the maximal entanglement I can have between the two systems. After that point, the radiation that I collect is so big and the black hole remained is so small that there's not going to be so much entanglement between the two, to the point that at some point all entanglement is gone. And because I have recovered the pure state. So one question in having a right setup where to understand the black hole evaporation is having a setup where I can show that I can capture the decrease in entanglement between these two subsystems at a certain point in my theory, in my description. And it's extremely difficult to find a way to quantify entanglement. And I think I've said that. Sorry. Reproducing the page curve would mean proving that your theory is the right setup, or at least has the right assumptions to describe black hole evaporation. And we expect our theory to have these to be correct, because nowhere in these in this description, in this evolution, we have gone outside of the regime of validity of our theory. Now, let me make one remark, which I think is interesting. So in the Hawking calculation of black hole temperature and black hole radiation, there is no difference between the solution of a black hole of mass m that is just started to evaporate, or the gravitational system of a black hole of mass m that was originally a black hole of mass 2m that has been emitted half of its mass through radiation. So in our classical theory, these two systems are the same. In the quantum theory, these two systems are very different. One of them is highly entangled with the outside radiation, and the other is lowly entangled, is weakly entangled. So you see that there is this new, entanglement is playing some role in this game. And it is only recently, I think, that we've understood, we're starting to ask many questions about how this entanglement can work. And the problem is to quantify the entropy of Hawking radiation. Is there any back reaction that we need to consider? How do we even pose the problem of what is the entanglement and how to quantify it? That's where holography comes into play, because we know that through holography, at least in a CFT, in a conformal field theory, the entanglement has a prescription for which is given by the extremal surfaces that I'm going to show. But again, the lesson here, I think, is that it is very important to understand the entanglement and its evolution, to know if we're in the right setting to describe a semi-classical black hole. There's a theorem by Mathur that's also very well established that is telling us that the structure of entanglement is non-trivial around the black hole. So if you assume, as I said before, that you need to have this radiation which is entangled with the rest of the black hole, how do you realize that once you assume that the black hole evaporation is due to pair production near the horizon? If you pair produce particles near the horizon and one particle is emitted and one particle goes into the black hole, those particles are maximally entangled with each other. But then one of these two particles is going to be part of the Hawking radiation that is the subsystem which will be maximally entangled with the rest of the black hole radiation. So there's somehow you're requiring too much maximal entanglement here to make sense of your description. And that was the content of Mathur's theorem. That was the first one to say, listen, we're not going in any out of any regime of the semi-classical gravity theory at the black hole horizon, but it seems we are. It seems you need a modification of your classical solution already at the horizon scale to be able to make up for a consistent unitary evaporation. And that's where was one of the motivation of his program to construct fuzzballs from string theory that are horizonless geometries with the same charges of black hole. Okay. What string theory did in the context of holography in recent years? Yes. With maximal chaos. Yeah. There's many. Well, on one side, it was interesting to see that fuzzball could reproduce something, but they've never reached the point where to actually explain black hole physics. Yeah, so it's a very active research thing, and there are properties of black holes that have been understood, like chaos, that are now telling us more about what are the features of black holes in a semi-classical regime, and we need to take those into account. Absolutely. I just have a short motivation for how it is important to or interesting to look at these questions from the point of view of holography and how it can be powerful. And one of them is really it allows us to compute entanglement in a simple way. It's if you look at in 2D CFTs, there's been developments by Cardi and Calabrese and Tonni that try to compute the entanglement entropy of a subregion in a CFT, and it requires a lot of technicalities. In some cases, you can have expansions at large charge, but in generality, you don't have a closed formula. And that's where, what does holography tell you? Holography tells you that if your CFT is holographic, so suppose you have this is the two-dimensional toy model of this B space. Imagine you also have time. If you have a subregion of a CFT that's in a certain state, then you can trace out the rest of the subregion, sorry, the complement of this subregion, and define the entanglement entropy of this subregion with its complement. This entanglement entropy of the state of the CFT in this region is captured by the area of an extremal surface that ends on the boundary of this region, that extends in a fictitious, in principle, higher dimensional space, that is the bulk of anti-de Sitter of this holographic CFT. So I have a CFT, and suppose if I am in the condition that I can couple it to anti-de Sitter holographically, then I have a prescription that is very reminiscent of the formula of the entropy of the black hole, that tells me that I can just extremize a surface in this bulk to find the entanglement entropy of the region of the subregion of the CFT. This was the first Ryuta-Kayanaji formula. And this is, you can imagine that this gives you a very powerful tool. You're like, oh, my black hole is emitting radiation. If the black hole was built in a theory whose matter was a CFT, a conformal matter, of a conformal field theory, then I can imagine that at infinity, this radiation will be in a certain CFT state whose entropy I can compute going to the holographic description. This was known, but remember, we don't just want to quantify the entropy. We want to quantify the entropy after the page time, when we need to start seeing that there's a mechanism for which the entanglement entropy starts decreasing. And that was the non-trivial progress that was made in recent years. What was important was first to identify that what's capturing this entanglement is this generalized entropy. In addition to this area surface, there's also a bulk entanglement between the fields of the region on the CFT and the bulk. And the second progress was to provide an example of where we could apply holography. Remember, holography means anti-de Sitter space. A black hole in anti-de Sitter does not evaporate, a large black hole. So we need to somehow construct a setup where this black hole is allowed to leak radiation outside of the ADS box. And this can be done in some by coupling these black hole through a higher dimensional setup in a sort of brane world construction. And what happens is that if you compute what is this extremal surface, it turns out that at late times, there is not just there is a new surface that is the one that minimizes this quantity, that gives you the entropy. But what is important is that this surface is disconnected from the radiation at infinity, and it can live inside the black hole horizon. And so these are well-defined quantum extremal surfaces, and they only appear at late enough times, consistently with what we expect, and they do have a lower entropy than the black hole. Let's say, sorry, they have a lower entropy than the Hawking calculation that had this curve. So it seems that we are in the correct setup to construct to describe black hole evaporation. We've given one example, but there's much more to understand. I'm almost out of time. All I wanted to mention is that these constructions are non-trivial. In some lower dimensional examples, one can do explicit calculation. In order to have higher dimensional constructions, one has to rely on double holography, basically brane world scenarios where the black hole live on the brane, but the holographic radiation is captured at the boundary in such a way that somehow this CFT is part of a holographic boundary where the black hole of a bulk where the black hole actually lives. And you can construct examples in string theory from the UV. You can work out quite simple solutions of intersecting branes, D5, NS5, and D3s. And you have ADS5 regions, which are where you have a dual conformal field theory, where you want to compute the entanglement. And you have an internal region, which is actually an ADS4, where you have your black hole that radiates. And we've done some work where we can show that we can construct these island surfaces, and their area actually provides the right setup to capture the lower entanglement entropy. Yes. So there are examples of trying to define these surfaces for four-dimensional black holes, but we don't have UV origin. We don't have a stringy construction of those. But the prescription in principle, and this prescription is holographic. So you need to have, you assume holography, yes. But somehow this black hole radiates. If you are an observer that collects this radiation and wants to compute this radiation, you are in a CFT that is in a flat space. So this was a trick somehow to have you see this. You're basically coupling the Minkowski-Penrose diagram to the ADS black hole Penrose diagram. It requires some, again, leaking of radiation, but it is a consistent model. I would say the signature that you derive is consistent. Then you can be like, okay, I have caveats here and there, but otherwise we would be like, oh, this is a black hole in the universe, and this is its entropy. It's not there yet, but it's a first very important example that I think has not ever been shown in the literature. And so I did not want to end with a summary and outlook, because I think that we are just too eager to discuss about and so I wanted to put just some questions that we can keep asking. So on one side there is this landscape that's been probed by string theory, and there's this Swampland emerging. How about Swampland from other approaches? Jan, in his talk, with his work, is also giving some progress in that direction. It would be nice to answer the question: do we have a single Swampland? Is there a Swampland universality, or different approaches give different predictions for the EFT? Can we discern among them in future experiments? At the level of black hole evaporation, I think so far string theory is very promising in understanding better quantum semi-classical properties of these quantum black holes, and understanding how to go beyond the Hawking approximation. I think that's a very interesting part. And again, what is the role of entanglement? Are we missing something? How to give a correct EFT that captures completely black hole evaporation? So that's it. Thank you very much. I'm already late.
Thanks, Alessandra. Okay, we have time for one or two questions. Let me start. Okay, once again, about the Matur theorem, you mentioned that corrections to black hole solutions should be order 1, even for large black holes. But couldn't these corrections somehow destroy horizons and then somehow modify a lot of the arguments that you presented at the beginning, if they are such order 1 correction, like big corrections to the black holes?
Arguments I provided at the beginning, meaning
like, for instance, everything that is based on evaporation. So if you destroy the horizon with order 1 corrections, then things could go wrong in some of the arguments, like charge completeness and no global symmetries and all of that.
Yes, but again, the problem there is that it's a principle. You need to change order 1, and then there are fuzzballs that can give you order 1 differences, and then they give you new predictions. And as Arkady was saying, well, when these predictions do not fit our semi-classical understanding, then it means they are not the right example, and there's not other examples. How do you, or at least I've not worked with other examples of black holes that semi-classically reduce to known black holes and observe, or that are consistent with observations and the properties that we know, that have order 1 corrections. And it would be, definitely. I don't know if you have examples of.
No, I mean, I was just that was also related to another question that I had, like, since you discussed that black holes are so important in the context of string theory or in general for the Swampland program, but I've also heard, like, in the context of string theory, wormholes play a role, fuzzballs, so there is really different solutions.
Fuzzballs are very, let's say, are order 1 different constructions, and that's a program by itself. Then again, it stops at that point. You stop looking at black holes. Like, you only look at the entropy of the effective black holes to reconstruct that. But from the original point of view, you don't want any singularity. That's your principle there is string theory resolves any singularity. However, wormholes are coming up, and I did not want to mention them because I didn't have enough time, but they are somehow believed to play a role as the gravity dual of these CFT computation. So the quantum extremal surface prescription is something that comes from holography, but if you had, in the end, it's a gravity process. And so what is the gravitational dual of this new saddle point that you see in or this new extremal surface that comes up at late times? So it's believed that actually in gravity, you have to sum over, you have to introduce new saddle points in the gravitational path integral beyond Gibbon's Hawking semi-classical approximation, and those will correspond to non-trivial topologies with a wormhole connecting them. And then there's many wormhole construction, but yes, they do play a role, but they are not in a different scenario.
Okay, thanks. Are there other questions?
Maybe. No, I think it's pretty obvious that after approximately half decay, the degradation should be order 1. Is this the theorem? I mean, I think it's obvious. You don't need anything. I mean,
No, but he was mentioning it is even for large, very large black holes. So where
Yeah.
arbitrarily large. That was
But then
my
do you think that
confusion.
the back reaction would be such that you destroy the gravitational description? So the Schwarzschild solution will not be good anymore, or?
so the Hawking computation is in exact semi-classical limit. And you can see, I mean, I think it's obvious that if there is no way to reconcile self-similarity of the black hole evaporation with the properties, because it's simply impossible. If we assume that black hole evaporates and shrinks and it becomes identical to a smaller black hole, there is absolutely no way to accommodate black hole properties and unitarity and this kind of stuff. So it's immediately clear that no matter how big is your black hole, latest by half it loses half of its mass, it can no longer be the quantum migration should be order 1. So that yeah, I don't know if that's the theorem. Yeah.
But then the problem is that we don't have that description.
Then the problem is how to account for this microscopically. But for this, you need a microscopic theory. So microscopic theory should be
But then at the page time, I'm already in the quantum black hole regime, and then I need to move away from.
Absolutely. Yeah. I think that is simply impossible to reconcile with unitarity and unitarity. So black hole operation cannot be self-similar beyond. By that time, for sure, we know that
Is it also the time where entanglement starts being high?
It would also formally coincide with the peak of the phases curve.
Yeah.
And by the way, what happens after that, we don't know. Nobody knows. And so therefore, how to really extend this curve? Again, you need to have microscopic theory. So without microscopic theory.
So this
There's going
seems to be a
time in
really good point, to start the discussion after the coffee break. So since we are running out of time, so let's thank Alessandra again for the nice talk. And